Hi, everyone. So this is another episode of Q&A, this time about science and technology for kids and others. So ask me whatever you want. We'll see what I know about. There were a few questions left over from previous sessions here, so I thought I might start off with a couple of those. So the first question we had was, what happens when you sneeze in space or turn on a flashlight in space? Okay. Let's talk about both of these. So first thing is, let's define sneeze where. Sneeze inside your spacesuits, sneeze inside the International Space Station, or sneeze directly into space. Let's hope it wasn't directly into space, because then you would be very cold, very much without air, and in very bad shape. But I think maybe what you were suggesting, let's talk about sneezing inside the International Space Station. Okay, so one feature of being in the ISS is that you're weightless. What does it mean to be weightless? So it means things don't fall to the floor. Normally when we're on the Earth, gravity makes things fall towards the center of the Earth. But when you're in the space station is orbiting the Earth. And so it's, in a sense, it's falling. And if you're inside the space station, you're just falling at the same rate as the space station. So relative to the space station, you're weightless. There's nothing pulling you down to the bottom of the space station, so to speak, because it's falling and you're falling with it. So for example, if you are in an elevator in a tall building and the elevator is accelerating downwards, you will feel not quite weightless, but you'll feel like you have less weight, because the elevator is kind of, in the bad case, the elevator might be just falling, completely falling, as if you just dropped the elevator. If you were in an elevator that was just falling, which wouldn't be a good place to be, then you would be weightless relative to the elevator, and you'd be just sort of floating around in the elevator. But in something like the space station, it's kind of, as it goes around its orbit, what the orbit is it's kind of, the space station is always falling towards the Earth, but by the time it would have fallen onto the Earth, it's already around the side of the Earth, and so it just goes around in its orbit. And so relative to that, you inside the space station will just be floating around, not being pulled to the floor, so to speak. Okay, so let's say you sneeze. Well, then what you're doing is you're taking, you're essentially, you could either sneeze or you could have a ball and you throw the ball. It's kind of the same physics that's going to happen. What's happening is there is this idea of conservation of momentum. That is, when if you throw the ball, you're making that ball have momentum going in a certain direction. And because of this principle of conservation of momentum, it will make you go in the opposite direction. So it's like, it's Newton's third law. You can describe it in a variety of ways. It's just a fact that's known about physics, that when there is, if you sort of are generating, if you throw something in one direction, you will recoil in the other direction, so as to keep the total momentum. Momentum is basically the mass. It's officially, in the simple case at least, it's mass multiplied by velocity. In order to keep that constant, if you push something one way, the thing that pushes it goes the other way. So if you were to sneeze, then you would be pushed the other way. Now, the amount you're pushed the other way, momentum is mass times velocity. And so your sneeze isn't a large amount of mass. It has a certain velocity. You're pushing your sneeze out at a certain speed, but it has a certain mass. It'll be quite small compared to your mass. So that means that because what's being conserved is mass times velocity, the math says that if the mass of the sneeze is, let's say, a gram, and let's say your mass is, I don't know, 100 kilograms, that means that you weigh 100,000 times as much as your sneeze. And so to conserve this mass times velocity quantity, that means you'll be pushed backwards a very small amount relative to by ejecting that gram of sneeze. Okay, so it's actually the same kind of deal with a flashlight. A flashlight is the bulb in your flashlight is producing light. Light is a stream of photons, and photons, like your sneeze, have a certain amount of momentum. The amount of momentum that photons have is quite small, but it is nevertheless not zero. And that means that in principle, you switch on your flashlight and it's starting, and it has a mirror that's making all of the photons be shone out forwards, so to speak, because that's what that parabolic mirror that you'll see in a flashlight is doing. The bulb might be having photons go in all directions, but the mirror is reflecting them so that they're all going forwards. So that means that the momentum of the light, the momentum of the photons, is all pointing in the forward direction. And so that will mean that there's a recoil of the flashlight by a very, very, very small amount backwards. Now, that very small amount of recoil, you can actually use that because this idea that there's momentum associated with light, there are places where you can use it. So actually, it was recently done to deploy a solar sail, a giant sheet of, I think, mylar, a giant sheet of reflective material, very light sheet of reflective material in space. You unfurl this thing, and then you shine light at it. Or, for example, you use light from the sun, but you might shine an intense laser light at it, or you might use light from the sun. Either way, there'll be a small amount of pressure. If the light from the sun, for example, is hitting the sail in that direction, the sail will be pushed a small amount along by that momentum of the light hitting it. And actually, there's sort of an idea. It's been in science fiction a lot, and a little bit of science fact now, of making solar sails, where you could, for example, tack out into you could sail out into the outer solar system, just pushed by the what's called radiation pressure, the pressure of photons from the sun hitting your sail. Now, the problem is the sun is not very bright. For us, it's still a reasonable, it subtends a reasonable angle in the sky. It's as big as our thumb or something if you hold it out. I think that's roughly right. If you were on even Mars, for example, the sun is much smaller, and as you go further out, the sun ends up looking like just a dot of light, like another star, and although somewhat more intense for anything in our solar system. And so this idea that you can use kind of light pressure from the sun looks a little bit less plausible as you go further out from the sun. So that was, this whole question of sneezes. Unfortunately, I've learned more than I would like to know about sneezes as a result of things about the virus. I'll tell you a few facts about this. So one question is, when you sneeze, you produce a bunch of droplets of water, basically. And those droplets, the most common size of one of those droplets is 2 microns, 2 millionths of a meter. So that's about, how big is that? That's relative to a period that you might see typed on a page. That would be about, let's see, that will be maybe 0.5 millimeter. That's 500 microns. So that would be about 1/200th of the width of the period printed on the page. That's the most common size for the big droplets that you generate when you sneeze. There are actually a whole bunch of much smaller droplets that you generate as well when you sneeze. What happens to the big droplets is they fall through the air. They fall just like if you threw a ball, it would fall. So these droplets similarly fall. They don't fall quite as fast as a typical ball would fall, because air resistance makes them, there's a lot more for a thing that small. It has the amount of force that comes from gravity versus the amount of force that comes from air resistance makes it fall less quickly. Actually, what's really weird is that when you sneeze, you generate a bunch of smaller droplets going down to maybe a 1/10 that size or less. And those much smaller droplets, they actually don't really fall in the air at all. In fact, they are continually, so okay, I have to explain one thing about so the air is made of a bunch of air molecules, nitrogen molecules, oxygen molecules. They're all bouncing around. And these molecules go, a molecule will be going in a certain direction. It goes roughly at the speed of sound. Each molecule in the air is going roughly at the speed of sound. But they don't go very far before they hit another molecule. I should be able to work this out. If I did a little bit of math, I could work out what's called the mean free path of molecules in air. I'm kind of thinking it's some fraction of a millimeter, I think, for air at standard pressure. So that means that these tiny atoms are going quite a distance before they hit another, or tiny molecules going quite a distance before they hit another molecule. Then they'll bounce off that molecule, and they keep bouncing. And when they keep bouncing around, they'll make what's usually called a random walk. They hit one molecule, they bounce off it, it bounces back. They go in kind of a random direction. So they go in a series of random directions. And that process of bouncing off molecules and going in random directions, it's often called Brownian motion, after a chap called Brown, who discovered it in the early-ish 1800s. And that was how people first understood that there were, got really good evidence that there were atoms. One of the two ways that people really understood that there were atoms was through seeing Brownian motion. Because what they saw was they had little tiny pollen grains, and they would look at them in a fluid like water or something, and they would see that these pollen grains would if you look at it under a microscope, they keep on getting kicked. And the fact that there were these discrete kicks was a sign that was something discrete in the water, some discrete molecules there, rather than just that it was a continuous thing. But in any case, so very, very small particles, water, droplets of water that you might sneeze, will be caught up in Brownian motion in the air. So instead of just falling like a ball that falls like a parabola to the ground, instead there'll be these little pieces of Brownian motion that will be just continually kicking that little tiny bit of water around, and it won't fall to the ground. It'll just stick around, and there are interesting videos people have produced looking at this. It'll stick around for hours. The thing that makes it not stick around is air currents. So as soon as there are air currents, like you open a window, poosh, the whole thing will be, it's a very light thing. So it will get any draft of air will just blow it around all over the place. So in any case, that's why, it's one of the reasons why people say it's worthwhile to kind of open windows and things to get rid of things that might be infected. By the way, if you're curious, the virus that we're all unhappy about is about 100 nanometers across. So that's about 1/10 of a micron, 1/10 of a millionth of a meter across. That's the size of the little coat of protein that encloses the RNA of the virus. And in fact, what happens is it will be in these water drops, and actually the water will evaporate away, and you'll be left with just this pure virus. And if you just had this pure virus in the air, it will be kicked around by Brownian motion. It will just stay in the air. The good news is, without a coat of water, I think the virus dies pretty quickly. So even though it's there in the air, you don't have to worry about it because it's not going to be able to replicate. That was a long answer to the question about sneezing in space. Okay. Okay. Okay, we have a question from John, age 14 here, about what is a hypersphere. Okay, so I think I showed an example before about things in more than 3 dimensions, but let me start off. You know, there's a really good example that I can show you. Okay, before we get to that, actually, I'll get to the other questions in a minute. Let me show you an actual example. I have a nice way to show this, which I think works really quite well. Let me just share my screen here, and let me pull something up. Let's see here. Okay, let me go like this. All right. So the basic answer to what is a hypersphere, it's a sphere in more than 3 dimensions. So, you know, we live, we think, in 3-dimensional space. What does that mean? It means we can go forwards, sideways, up, you know, forwards, backwards, left, right, up, down. Those are 3 separate directions that we can go in space. We can't, if we lived, if we were kind of little creatures that live just on the surface of on a plane, on a surface, we might only be able to go in 2 dimensions. We would only be able to go forwards, backwards, left, right. We wouldn't be able to go up, down. We couldn't get out of our plane, so to speak. But so a question is, what happens if we, is it possible to have more than 3 dimensions? So in our universe, right now, so far as we know, we basically live in a 3-dimensional universe. You know, I've sort of it's a strange thing, but I happen in recent months to have been working a lot on sort of fundamental theory of physics, and that, which I'm going to be talking about a bunch more probably next week. In that theory, there are a lot of these questions like, why is space 3-dimensional? We actually get to have answers to those questions. And actually that theory suggests that there may be little perturbations where space isn't exactly 3-dimensional, and they may have all kinds of consequences for our universe. But in a first approximation, the way we experience things, space is 3-dimensional. Okay, what does it mean to be 3-dimensional, 4-dimensional, whatever? So here's a way that I've found that's quite useful to kind of see this. Okay, so this is, oops, I typed the wrong thing. Okay, so this is a grid, and we would normally say this is a 2-dimensional grid. It's 2-dimensional because we can go left, right, or we can go up, down here. We could as well have a 1-dimensional grid, which is just where we can just go left, right. We can't go in any other direction. So this is a 1-dimensional grid because there's just one direction we can go in, one independent direction we can go in. It's 2-dimensional. So now let's do, let's make a 3-dimensional one of these. So we can say, make a grid, a 6 by 6 by 6 grid. And now we have, let's see, I can probably make this, so it's obviously 3D. This is, okay, so here we have something which we can rotate around, and we can see that it is what we would normally call 3-dimensional, okay? But let's take a look at the actual structure of these things. So let's say we'll make a square like this. And in the square, from every corner of the square, there are 2 neighboring corners, 2 neighboring points. Let's do the corresponding thing in 3D. So if we do, so this is a 2-dimensional square. In 3 dimensions, we have a cube. And in that 3-dimensional cube, if we look at each corner of that 3-dimensional cube, it is adjacent to 3 other corners. So that are in the, like, often these directions are called the X direction, Y direction, Z direction. Up, down, left, right, in, out, for example. Okay, so the obvious thing we might do is to say, great, that's a 3-dimensional, well, this would be a 3-dimensional cube. What would a hypercube look like? What would a 4-dimensional cube look like? And so we can just say, show us this thing that connects where we're making something in which every corner effectively is connected not to 3 other corners, but to 4 other corners. Okay, so this object has the structure of a 4-dimensional cube, often called a hypercube or sometimes called a tesseract. This thing has the structure of a 4-dimensional cube. Now you can see it's every corner is joined to 4 other corners. Now, if we can draw this thing, we can draw a representation of this in, here I'm drawing it just in 2 dimensions. I could make this a 3-dimensional representation, and I could then rotate it around. And this is kind of drawing in 3 dimensions something which is in a sense really 4-dimensional. Just like if you make a picture of a sphere, for example, you can draw a picture of it on two dimensions, where you might use shading and things to give you a hint about what's happening in the third dimension. So similarly, what we're doing here is we're drawing a four-dimensional object, and we're rendering it, well, ultimately in two dimensions, but I'm showing it kind of as a three-dimensional thing here. So that's what it means to have a four-dimensional hypercube. It's a thing where every corner on a cube, every corner has three corners adjacent to it. On a hypercube in four dimensions, every corner has four corners adjacent to it. And we can have a five-dimensional hypercube where every corner has five corners adjacent to it, and so on. So that's how we would invent these objects, which we can think about mathematically in more than three dimensions. Now, in the case of a sphere normally is something that exists in three dimensions. A sphere is the set of points you get where you start from the center, and then you just say, what are all the points that are the same distance away from the center? Okay, so like a sphere of radius 1 would just be a thing where you're looking at every point in three-dimensional space that is a distance 1 away from the center. You can do exactly the same thing in four dimensions. You can say, make me something where I'm looking at all the points that are, let's say, distance 1 away from the center, but not in three dimensions with three coordinates, but instead in four dimensions. So that's what a hypersphere is. And you may know the formula in three dimensions. The volume of a sphere is 4/3 pi r cubed. That's the formula for the volume in three dimensions. There is similarly a formula for volume in four dimensions. But let's actually talk first of all about the volume in two dimensions. The volume in two dimensions is actually just the area in two dimensions. So for a circle, the quotes volume of a circle, which happens to just be its area, is just pi r squared. So there's this sequence. In two dimensions, the formula is pi r squared. In three dimensions, it's 4/3 pi r cubed. And so you might reasonably guess, you might wonder, what is the volume of a sphere in d dimensions? And let's see if I can say volume of d-dimensional, well, let's call it a d-dimensional ball. Let's see if we know that. Not looking promising. Let's see. I think I should just type it directly into Wolfram alpha. Well, but I can do. Let's do this. Hold on here. Let us go to Wolfram alpha. Here we go. Let's say volume of 4D sphere. And this is going to, tricky. Okay, so when mathematicians talk about this is a tricky thing. Okay, mathematicians, when we talk about a sphere, when we're not doing fancy math, we usually mean a thing like a ball that's just this sort of solid object that is round, okay? When mathematicians talk about what they would call when mathematicians are talking about this ball, they usually call it a two-sphere. Why do they call it a two-sphere? They call it a two-sphere because its surface is two-dimensional. The whole volume is three-dimensional, but its surface is two-dimensional. And it's as if you took a plane, a flat two-dimensional thing, and rolled it up. Then you get a two-sphere, so-called S2. So when they talk about this is saying, assuming a sphere in five-dimensional space. Actually, we want a sphere in four-dimensional space. So what I'm going to show you here, this is the volume of a sphere in four-dimensional space is pi squared r to the fourth over 2. So it's pi squared over 2 r to the fourth. So that's the analog of 4/3 pi r cubed in three dimensions is pi squared over 2 r to the fourth. And for people who are, if you really want to get fancy, see if we know this, we do not know. Let's see, if we say d-dimensional sphere, I wonder whether we'll know what we're talking about here. There's a formula. No, we do not know what we're talking about there. Okay, there is a formula for the volume of a d-dimensional sphere, which comes out in terms of factorials. It's always r to the d, but it's multiplied by the factor that will be 4/3 pi in the case of 3 dimensions, and is pi squared over 2 in 4 dimensions, is a different factor in different numbers of dimensions. And actually, let's see how we can compute this. Well, I could go look it up because I know where I've written it down. Let's see. I will just see if I can get a good answer here. Here's a good place to get it from. Oh, actually, yes, our Math World site has a nice thing on it. Okay, so one of the things, let me show you one thing. So this is all fancy calculus that allows you to work out the volume of a d-dimensional sphere. Here's one little interesting fact. So that prefactor, the thing that for a circle, a disk, is just pi r squared. It's 4/3 pi r cubed. For a sphere, it's pi squared over 2 r to the 4th for a 4 sphere. That prefactor, that thing with pi's in it, you might think, oh, as you increase the dimension, that will always increase or decrease or something. Bizarrely, that prefactor actually has a maximum around, I think this is saying 7 dimensions, 7.2 dimensions. Just a weird math fact. Okay, let's go back to, so that was sort of an explanation of what a hypersphere is. Let's see, I think what else to say about hyperspheres? I would say that we don't know, at a mathematical level, it's all fine to make hyperspheres. We don't know if one can make those physically in the universe. We don't know if, for example, the whole universe could be, our 3 dimensions could be wrapped around a higher dimensional sphere, potentially. Okay, let's see. There was another question here. Is a single virus enough to get you? Probably the answer to that is no. Probably the answer is it's thousands to even millions of virus particles that you need. There is some, from what I gather, there is, okay, so what happens is once the virus infects one of your cells, it kind of takes over that cell and it starts replicating itself. And so what happens is, first there will be 1 virus, then there'll be 2, then there'll be double that number 4, then there'll be double that number 8. And the number of viruses, if your immune system or something else doesn't go attacking it, will roughly double every, I don't know how fast this virus replicates, every 30 minutes, every hour, something like that. And so it increases exponentially, doubling all the time. So you might think then that, well, it doesn't matter. If you just start off with 1 virus, then it doesn't take very long to get to 1,000 viruses. I happen to know that 2 to the power 10 is 1,024. So that means that after 10 replications, from starting from 1 virus, you would have 1,000 viruses, 10 doublings, you'd have 1,000 viruses. So you might say, why does it make any difference if you start off with 1,000 or you start off with 1? I don't completely know the answer to that. I think that it is likely that, well, there are defenses that your body has, and also just the probability, the chance that a virus successfully gets into a cell is certainly not 100%. There is some medical evidence last few weeks that you get more sick if your initial ingestion of viruses is with a larger number of viruses. I don't really understand how that would work, although maybe there are some arguments about the way your immune system attacks the virus and sort of how the competition between your immune system attacking and the number of viruses replicating works, but I don't completely understand that. But the answer is 1 tiny virus particle shouldn't cause you trouble. Okay, question here from Paulo. What is the most curious property of prime numbers? The most curious property of prime numbers. There's so many curious properties. Well, here's one that I was surprised by recently. So if you look at, so prime numbers, numbers that only have what you can't divide exactly by anything except 1. So numbers like 7, 11, but not numbers like 9 and 10, which can be factored. So the fraction of numbers that are prime gradually decreases as you increase the number. It goes down roughly logarithmically. But one question that I happened to notice a while ago, if you look at the average distance between primes for numbers, for fairly small numbers, like numbers less than 1,000 or something, the average distance between primes is 6. Okay, the most common, that you get a different distribution of distances, and the most common is 6. So like 11, well, the next one is 13, but if it was 17, that'd be 6 apart. Okay, so you might have thought, okay, so for numbers less than, let's say, 1,000,000, the most common difference between primes is 6. Okay, you might have thought that will last forever, but it doesn't. Gradually, as you get to larger and larger numbers, the average distance between primes gets a bit bigger, bit bigger, never stops. Actually, okay, I'll mention another property of primes that you might find fun. So I mentioned that the density of primes gradually decreases as you make numbers bigger. The fraction of numbers that are prime gradually goes down. It goes down like the logarithm of the size of the number. The logarithm is just if you are saying, let's not talk about what that is. I'll just say that the logarithm to the base 10 of 1,000 is 3. The logarithm to the base 10 of 1,000,000 is 6. 1,000,000,000 is 9. It's the number of times you're multiplying by 10 to get to the number you want. That number of times you multiply is the logarithm of the number, and so that means you can get to a very big number without and still have a fairly small logarithm. Okay, so there's a fact about prime numbers that the number of primes, the density of primes, is always, and I'm not going to get it the right way around, is always either less than or greater than this thing that's given by this logarithm. And that's true for any reasonable size number. You work it out on a computer, you'll find it out it's true. But actually, there are numbers that are for incredibly huge numbers like 10 to the 10 to the 100. That's like a 1 with a 1 with, let's see, a billion zeros after it. So a very big number. For a number that big, this fact about the density of primes flips around and it's no longer true. So it's really surprising that there can be something that is sort of just talked about in terms of primes, where it's true for numbers up to even absolutely huge numbers, but it isn't always true. And it's an interesting fact about math that things like that can happen, that you can think something is true for almost every number, for numbers up to huge sizes, but until you've actually got a formal proof, something where you can just deduce from this step to that step to that step that it's true, you're not sure it's true for every possible number. And that's a lot of the effort in pure mathematics has to do with making these proofs. They teach small versions of those in school. The reason that proofs of things that might seem obvious are still worth doing is that you might, to sort of deal with the really infinite case, you need one of these proofs. There are lots and lots of other properties of prime numbers, but let's go on to something else. Okay, there's a question here. Do you think kids should approach computers as if they're magic, or we should encourage them to understand how they work? And does this apply to things like Mathematica? One of the things that happens in sort of human progress is that we automate more and more stuff. There's more and more things that we don't individually ourselves have to do. I mean, back in the day, let's say you wanted to write something on a piece of, well, you didn't have paper. Let's say you wanted to write something on a wall of a cave or something like this. Well, in order to do that, you'd have to make your own paint, and then you'd have to, go and figure out where it's going to be painted, how long it's going to last, all those kinds of things. The progress of civilization and technology is all about kind of automated things like that away, so that we can kind of take for granted that a bunch of stuff works, so we can kind of concentrate on the next things that haven't yet been figured out how to do. So, there was, I think it might be surprising to people that the fraction of people in the world who grow their own food has gone dramatically down, for example, in the past century. It might be that, one would expect that if you want to eat stuff, you'd have to grow your own food. But we have this whole infrastructure, a whole mechanism for sort of, in a sense, automating that away as part of civilization. So similarly, if we want to work out the answer to some, let's say, math problem, well, how did one do it? And the first people who we know did a lot of elaborate math problems were the Babylonians. And we know, starting about 4,000 years ago, that there was people did school math exercises, and these school math exercises are interesting to look at from the Babylonians because they're unbelievably similar to the exercises that are done today. The only difference is that some of the stuff they talk about bushels of or amounts of barley and things like that, maybe in most parts of the world, those aren't the common version of word problems in math. It's really fun to look at what kind of Babylonian school children, so to speak, did. The Babylonians are a civilization about which we know a lot because they had this special feature that they wrote things down on clay tablets, and those clay tablets are well preserved. And so while there were a bunch of other civilizations that probably existed at the same time, they didn't have written records that we now have. But for ancient Babylon, we have lots and lots of these clay tablets, and these clay tablets describe lots of things. For example, they describe math, and they have in their mathematics, we use base 10, for example, to represent numbers. So like the number, 123 is 3 units, 2 tens, and 100. For the Babylonians, they used base 60, which means their units that represented ones, their next were represented 60s, and their next represented 60 times 60. Well, you might notice that one vestige of Babylonianism that still exists in the world today is the way that we count time, and that comes directly from the Babylonians, the fact that there are 60 minutes in an hour. I'm not sure if the Babylonians had seconds. The fact that there are 60 seconds in a minute, this is the Babylonian number system shining through into modern times. But the Babylonians had pretty sophisticated stuff that they did with numbers, and they understood, they were very, very obsessed with reciprocals, 1 over a number, because they had a way of calculating things that involved that. And they wrote out tablets of tables of reciprocals and so on. But anyway, back in the time of the Babylonians, if you wanted to do a piece of math, you were really doing it. You were perhaps sometimes there's some scratch work that's even preserved in these clay tablets. Sometimes there are exercises that people did on these clay tablets 4,000 years ago where we can say today, whoops, you got that a little bit wrong. But we know that we know kind of how the math was done even at that time. They had very elaborate math. I've actually recently learnt they had a whole scheme for computing the position of the moon. And that scheme was based on having sort of functions that were in zigzag shapes and adding together lots of different zigzag functions to figure out where the moon would be. Very similar, if you are aware of the history of science, to the way that epicycles worked in the Ptolemaic system for understanding the solar system. Actually, in today's world, when we compute the position of the moon, we're doing it in a computer using where we add up series of 10,000 different things that are a little bit like the Babylonian zigzag functions. But they actually had a whole procedure for computing the position of the moon, very much like our programs today. But that's something that was sort of lost over the course of the millennia until more recent times. But in any case, so back in Babylonian times, you want to do some math, you're doing it yourself. Well, steadily there were various kinds of tools that were invented back when I was a kid. There were things called slide rules that were these things. I would get up and go fetch my slide rule but let me just sort of explain how they worked. They were just these things where you have these two things that slide back and forth that have scales a little bit like rulers on them, but they had a little clever feature. The rulers were marked actually using logarithms, and the way things work, when you add logarithms, that corresponds to multiplying numbers. And so it's like when you slide these slides and you read off what number is on top of what other number, you can use that to figure out what the multiplication of two numbers, what the product of two numbers is. So back when I was a kid, believe it or not, people were still using slide rules, and it was like, how fast could you do it? And it was a very manual kind of thing. There were also mechanical calculators that used cogs and gears and so on to do arithmetic. Then around 1970, electronic calculators came in, and things changed very rapidly, actually, in a few years. So nowadays, you want to do a piece of, let's say, mathematical calculation, you don't have to do it out by hand and work it all out. You can just use a calculator or a computer to do it. And, that is progress. And the fact that you can use a computer to do it means you can do 1,000,000 pieces of arithmetic. And when you do 1,000,000 pieces of arithmetic, you can make all kinds of fancy things out of it. You can make all kinds of interesting pictures. You can try to understand what's going on and so on. So I would say that the main thing to say is that it is the great thing, in a sense, about the progress of civilization is that we build this taller and taller stack of what's automated. Now, you can ask, is it worth knowing how a computer works inside? It's a pretty specialized thing to know how a computer works inside. I think it's pretty interesting, but it is a pretty specialized thing. Just for fun, maybe I'll talk a little bit about how a computer works inside. Back even a few years ago, you could readily take computers apart. It's become more and more difficult to take computers apart. I don't recommend you do this. Don't do this. Kids, don't take apart some computer because you won't be able to put it back together again. At least the manufacturer will never touch your computer after you've opened it up and things. But particularly for desktop computers, you potentially can take them apart. It's more difficult with laptops. What will you see if you take a computer apart? Well, you'll see a bunch of you'll see typically a printed circuit board. That's a thing where they're essentially a bunch of wires that have been sort of printed onto a board to carry electricity between different places. And then you'll see these chips, these things that you'll see probably the plastic coating of the chip, and you might see a whole bunch of pins that stick out of the chip on each side. That's the main heart of the computer. The central piece of a computer is called its CPU, its central processing unit. That's the thing that sort of does most of the computing in a computer. Okay, what is a central processing unit and how does it work? If you were to slice the top off that, it's contained in plastic, but if you were to slice the top off and do it very, very, very carefully, because usually these things are, for a variety of reasons, they're made so that they're pretty hard to slice open and look inside. If you looked inside, you would see a kind of a dull metallic thing, maybe, I don't know, a couple of centimeters across typically, and might look like pretty much nothing. But if you would look at it under a powerful microscope, you would see something that looks like a city map, but a city map which kind of on the scale of streets that would be in a typical city, it would be like city map covering the whole Earth. It's a lot of little tiny streets going all around different places, and that is the circuitry that is what operates the computer. How does that circuitry work? Well, you'll see if you looked at the CPU chip, you would see different sections. So one section that's reasonably easy to understand is the memory of the computer. That part of the memory, well, there'll be on the CPU chip, there'll usually be some local memory, some local RAM, local random access memory. And what is that? Well, what that's doing is it's storing all kinds of things that you're computing. So for example, it might be storing all the pixels, all the colors of pixels that you're going to put on the screen at the next moment. Or it might be storing the words that you have in a document that you have in a word processor. It could be storing any kind of data. So one of the things that sort of makes computers work is that all of this different kind of data that we look at, whether it's an image on the screen, whether it's text, whether it's audio, all these different kinds of things, at the level of the computer chip, they're all ground down into just individual bits. So, for example, and the way that works is that in the end, the way computers store things is they basically store kind of like numbers. At the lowest level, they're just storing zeros and ones, but usually those are clumped together in what are called bytes. And a byte is 8 bits, 8 zeros and ones. And in 8 zeros and ones, you can store any number from 0 to 255, 0 to 255. So the bytes in a computer are basically storing numbers between 0 and 255. And in your computer, like, well, my computer, I think, has about 100 gigabytes, 100 billion bytes. The one on my desktop, at least, has about 100 billion bytes of memory. And so that means it can store 100 billion bytes of data. So, for example, your screen might be, if it's a reasonably high-resolution laptop screen, it might have, let me just work it out, it might have it might correspond to a few million, maybe 10 million bytes of data to represent for every little pixel on your screen what color it is. Might altogether take 10 million bytes or something like that. And so anyway, ultimately, all of this data, whether it's data about pictures, data about words, whatever, is stored in bytes as these bits in the memory of the computer. So, for example, if you want to take text, every letter is assigned a certain number. So in the usual way of doing things, I think a lowercase a is assigned the number 65, and the lowercase b is assigned the number 66, if I remember the numbers correctly. Maybe that's a capital A. I have to look it up to be sure. But there's a sort of standardized code for every letter. So actually, for letters just in the standard English alphabet, they all fit in a thing called ASCII, which just uses 1 byte to store each letter. There's a fancier thing called Unicode, which was invented in the 1990s as a way to store all the characters that show up in all of the languages that exist on Earth. And you know, there are characters in languages like Chinese, for example. There might be, I don't know, 40,000 characters instead of our usual 26 letters of the alphabet. And there might be in other languages, there are similarly, well, there are a few other languages that have it, usually CJK. Chinese, Japanese, Korean are the ones that have tens of thousands of characters that need to be encoded in this Unicode way of specifying characters of text. And actually, so standard Unicode stores a character in not just 1 byte, but 2 bytes. And that allows you to get the characters that exist in that number of bytes. You have altogether 65,000 possibilities, so you can store 65,000 different characters from the different languages of the Earth. And it doesn't quite get everything. Actually, our friends, the Babylonians, I was just mentioning, who their cuneiform that they used for their writing system didn't fit in ordinary Unicode. So actually, there's an extension to Unicode that allows you to make sort of extra versions of this that, for example, will fit cuneiform. Or actually, in modern times, the real win of what's called beyond plain zero Unicode is fitting emoji, because there are lots of emoji and people want to put even more emoji in. And to specify all those different emoji, you need a larger number of slots in your character set. And so there's been an extension to do that. Okay, back to computers and storing things. So all these things, whether they're characters, emojis, things on the pictures on the screen, whatever, these are all eventually stored as data, stored in bytes. Within each byte, there are 8 bits. Each bit is just a 0 or a 1. Okay, so ultimately, when you look at this computer chip, you will see this big area of the chip that's just a giant array of little elements, and each of those little elements stores just 1 bit. And what it's doing is Each of those little tiny elements is saying whether a particular some particular piece of data for your computer is a 1 or a 0. How does it store that? Okay, slightly tricky. Let's see, where do we go here? I mean, okay, I'll explain. There are different forms of computer memory. So ordinary memory of a computer, ordinary RAM, random access memory, it's called random access because you can go and say, I want the piece of data that's at that location in the memory. For any location, you can immediately pick it up. The reason it's called random access is back in the day, a long time ago, when people, well, actually, okay, when people were using tapes, magnetic tape, to store things on computers, you might see in old movies, you'll see, you'll sometimes see the computer room, and there'll be these things that are, these circular things that are twiddling back and forth. Those are tapes, and they're just a long, if you unspool the thing, it's a big long, big long thing of tape, magnetic tape, and that's not random access memory, because if you want to know what was at the other end of your tape, you have to unspool the whole thing and to put it onto another spool of tape to go find that piece of memory. So that's not an example of random access memory. But so modern computers, their main memory is what's called random access memory, because you can just get a piece of data out of anywhere you want in the memory, without having to spend lots more time to get it from another part of the memory. So in typical random access memory, it requires that the power be switched on your computer for it to keep its memory. There's another, it's rather confusing, all the terminology, ROM, read-only memory, and there's also other things like EEPROM, erasable programmable read-only memory. All these abbreviations, but that is something which, even if you switch the computer off, it will store its 1s and 0s. But it actually works in more or less the same way as ordinary RAM. Okay, so how does RAM work? How does computer memory work? Okay, let's see. Let me say the big picture first, and then we'll go into more detail. So every bit in computer memory is stored using a collection of transistors that are implemented using using the properties of the element silicon as a semiconductor. Okay, that's kind of complicated, but let me try to explain. Essentially, gosh, this may not be so easy to explain. Essentially, what's happening is that, well, all right, this isn't quite right, but you can kind of think of it as the, no, I'm not going to, okay. Let me put this to the side, because it requires a little bit of level of explanation of how the memory is maintained. But basically, what's happening is that in a very rough approximation, you've kind of got electrical signals that are just sort of recirculating around, and they just keep recirculating around. And when it represents a 1, there's an electrical signal there, and when it represents a 0, there isn't. That isn't quite right, but that's a first approximation. But let me explain more about what's on this silicon, what's on this chip. Okay, so that thing that I said was kind of like a giant city map. That's essentially a bunch of wires that are connecting data together, that are implementing all the operations in the computer. So let's see, how to explain how this works. Okay. Let's talk about, first of all, what operations a computer fundamentally does. So when you type in, let's say you type into Wolfram language or something, 2 + 2, what does it actually do? What it's actually doing in the end is it's running kind of a, that 2 + 2 that you type in is translated ultimately into a long string of what are called machine code instructions, the instructions that the computer intrinsically knows how to do. So it's an incredibly fundamental fact that you can have a fixed machine code for a computer, and you can, just by writing different programs, you can have the computer do a whole range of different things, whether it's running a video game or being a word processor, all these different things. It's the same underlying machine code instructions that the computer has available to it. It's just the program that you've given that says what sequence of machine code instructions you're going to run that's different between the video game and the word processor. And that's a fundamental fact. It's this fact that the existence of universal computation was first discovered in the 1930s, wasn't really made use of until the 1950s. That's a fundamental sort of mathematical fact that's basically what makes modern computers possible, what makes software possible, and so on. If that fact wasn't true, then the thing you would need to run, let's say, a word processor or a math computation system, you'd need to just buy a different computer, because it would have to have different machine code instructions to do all those different things. But this fundamental fact that universal computation is possible means there's one set of machine code operations, and it can be programmed to do all these different things. Okay, what are the machine code operations? So they're very low-level things. They will typically say things like, well, for example, actually adding numbers is probably a machine code operation. But a more typical operation says, get this number from this location in memory and get another number from another location in memory, add them together, put the result back into another location in memory. Or another operation that's very important is just go through the program that, okay, so another critical fact about computers is they can store data like what's on your screen or what's in your document. But one of the kinds of data they can store is programs that tell the computer what to do. Programs can also be represented as data, just like the things on your the words in your document can be represented as data. So also the program that tells the computer what to do can be represented as data and stored by the computer. And so one important operation for the computer, one important sort of machine code operation, is just go to the next thing, the next instruction that's written down in your program, and go do what that instruction says. And so then another thing is to say, I've got to this instruction, now jump back to a previous instruction. That's something that allows you to make a loop for the computer. Now, honestly, when you are thinking as a human and trying to program a computer, you don't really want to be down at the level of saying, I want this instruction to be executed next, and then I want it to go back and jump to this other one. The further away you are from all of that detail, the more you're going to be able to program interesting things. But as far as the machine code of the computer is concerned, it's operating at that level of saying, do this instruction, do this next instruction, pull this data from one place in memory, add it to another thing. So in a typical computer, there are different styles of computer, so-called reduced instruction set and complex instruction set computers. But in a typical modern computer, there might be maybe, let's say on average, 100 machine code operations, 100 fundamental things the computer knows how to do. And so when it sees its program way down at the level of what's stored in its memory, what it will see is an opcode that says, do operation number 17, which might be subtract numbers from each other or something. Do operation 17 on memory location 67584 and memory location such and such, and put the result in memory location such and such. That's ultimately what the computer is doing at the level of what's called machine code. Okay, so I mentioned that there's memory in the computer. There's also another piece to the CPU, which is usually called the ALU, the arithmetic logic unit. And that's the part that doesn't just store things, but computes things, actually does the addition and so on. It's the part that actually executes these opcodes. It actually does the operations that are specified by the opcodes. Okay, so how does the ALU work? Well, it's a big, really complicated circuit. And over the course of the last 50 years, basically, people have built bigger and bigger and more complicated circuits. So they have billions of components now. And it's been found out what the most efficient ways to like add numbers together in bits and so on are. And so that ALU is the thing that is all those little tiny sort of wire-like things that you would see if you looked at a chip under a microscope. And how does it actually work? Well, at the lowest level, all a computer is doing is a single operation over and over again, and the results from that operation are being fed into other places and being taken to other places and so on. And the one operation that any modern computer does over and over and over again is a thing called NAND. Okay, so let's explain what that is. So we have to explain a little bit about logic first. NAND is a logic operation. Okay, what is logic? So if we say logic is kind of a way to represent, sort of idealized way to represent statements that you make about the world. At least that's one way of thinking about it. So for example, if I might say, let's say, if it rains today, what's a good example? I might say, my phone cover is red, or my phone cover, or my phone is either red or it's black. And that's, so I can think of that as the statement, my phone is red, my phone is black. Those are two statements. I might call those statements P and Q. And I can then think of it as a piece of logic that is P, my phone is red, or Q, my phone is black. Then I can do, I could say P or Q, my phone is red or my phone is black. Or I could say P and Q, my phone is black, my phone is red, and my phone is black. And there are things that we can, operations we can do. We can say things like, it is not true that my phone is either black or red. If that is not true, then it follows that it is not black and it is not red. Can go through that again. So this was invented, this whole idea of logic, at least as far as we know it, was invented by Aristotle in the 2nd, 3rd century BC. And it's something used to be taught along with math, as it used to be one of the big subjects that was taught a few hundred years ago in school. Math really won out relative to logic. But logic is these kinds of things where you say, consider a statement, my phone is red, and call it P. Consider another statement, my phone is black, call it Q. And then we can sort of do operations on that that are a little bit like algebra. There's a version of algebra called Boolean algebra, which is sort of an algebra for logic that works differently from the algebra that you do for numbers. Okay, why am I telling you all of this? Because inside a computer, so I mentioned and, I mentioned not. Inside a computer, the operation that is implemented over and over again is the not and operation, usually called NAND. And so what that means is that what it means to implement it is there are essentially wires that come in, and you're saying that the wire either has electricity on it or it doesn't. So that corresponds to it either has a 1 or a 0. The other wire has either a 1 or a 0. If we were doing the AND operation, we would be saying two wires come in, they can either be 1 or 0, and we say the AND operation would be the result is a 1 if both the first wire and the second wire have 1s on them. And the OR operation would be the output wire is a 1 if either one wire had a 1 or the other wire had a 1 on it. Okay, so the NAND operation happens to be, it is not the case that both wires have 1s on them. Okay, seems like an irrelevant kind of weird thing. Okay, NAND that seems like kind of a weird thing that might be a footnote in a book about logic. And actually, when NAND was first invented around 1900, that's kind of how it was. But then it turned out that people discovered that it was possible to use semiconductors type of material to implement NAND operations, to actually make it so you could make these wires and have it be the case that when the wires come in and they have 1s and 0s on them, that what comes out is the not and of what went in. Okay, how are those wires implemented? How are those things implemented? They're implemented using things called field effect transistors in silicon. I can explain more or less how this works. Roughly what happens is, gosh, I'm explaining a pretty big technology stack here, but let me keep going, because I think I can more or less get all the way to telling you how a computer works. All right, let's imagine we have a wire and it just has an electric current going through it. So it has little electrons that correspond to the electric current, and they're flowing from one end of the wire to the other. Okay, let's imagine we have another wire that's sort of crossing over that wire, and we have it be the case that if there is a voltage, if we sort of put a battery across that sort of wire, that wire that goes across, then we can, with that voltage, if there is a voltage there, it will, let's say, prevent a current from going through this wire. If there isn't a voltage, it won't prevent it. Okay, so this essentially makes a switch. We've essentially made an electrical switch where by saying whether there is voltage on one wire, we're determining whether current can go through the other wire. Okay, now it turns out that with a combination of a few of those switches, we can make a thing where we have a pair of wires and it will make a NAND gate, as it's called. It's called a gate because it's kind of like you're opening and closing a gate depending on whether this voltage is there or not. Okay, so, all right, well, so essentially what we're trying to do is we're trying to make these NAND gates. And well, first thing to say is, why do we care about making NAND gates? The reason we care about making NAND gates is NAND is a logic operation that has an interesting property, that if you combine together NAND operations, you can make any other logic operation. So I don't remember what it is, but I think if it's NAND of P and NAND, P NAND Q or something, let's say, is the equivalent of P and Q. I don't think that's quite right, but it's something like that. But so by combining NAND operations together, you can make any other logic operation you want. And so in the circuitry of a computer, every operation, the whole ALU, is just made as a giant combination of NAND operations. That's all it's doing, is billions of NAND operations, which are all being combined to make all the operations you want, to add numbers together or whatever else. Okay, so explaining how NAND actually works. So you've got these things, they're called field effect transistors, FETs, that are the actual thing that has electric currents going through that are controlled by voltages. How do you make one of these transistors? Well, it's kind of clever. Okay, a little more explanation, a little bit of physics here. So, okay, chemical element, silicon, very common chemical element. Rock is made of, the primary thing rocks are silicates. Silicon is a core piece of any rock. Okay, if you make silicon very, 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 very pure, you can make crystals of silicon that are more or less perfect crystals, where the atoms of silicon are perfectly lined up at an atomic scale. And usually silicon doesn't conduct electricity. So metals, for example, like, I don't know, copper or something like that, it conducts electricity. You can make a wire out of it. You put a battery across it, and it will make an electric current flow through that wire. Silicon doesn't have that property. An ordinary lump of silicon doesn't conduct electricity. But it is a semiconductor, and well, there are all sorts of different ways. It's just on the edge of being able to conduct electricity. And so there are all kinds of detailed things you can do to make it conduct electricity. So one of the things you can do is you can dope it with a very small amount of some other material. So there are these different kinds of dopants, which are other chemical elements, and you put tiny, tiny concentrations of these into silicon, and they cause the silicon to essentially be able to conduct electricity under certain circumstances. And essentially what you're doing when you make one of these little switches, one of these field effect transistors, is you make a little pattern of doping where you have a little bit of, like, I don't know, indium, I think, is one of the dopants. I think maybe tin, maybe a dopant. I'm not sure. There are all kinds of different chemical elements. It's kind of a zoo of chemical elements. You know, you see this whole periodic table and you say, what would anybody possibly use, you know, indium or something for? Well, tiny amounts of it are used as pieces of sort of random what element is useful, because it depends on the atomic properties of the element, what element is useful to dope silicon with. So okay, so then what you're doing is you're putting in these little tiny amounts of these other elements, and they change the electrical properties of the silicon and allow you to create these things like field effect transistors, these little tiny switches, which then can be assembled into little tiny NAND gates, which can then be assembled after you have 1 billion of them into a great big ALU. So, okay, so how do you actually make this? So that's what this giant sort of cityscape is. It's all the little tiny places where there is and isn't dopant on the silicon, where there is and isn't a piece of that kind of wire that goes through. And I'm eliding a lot of details of how semiconductors get made, but that's roughly the idea. So then the next question is, how do you actually make, in a 2 centimeter square, how do you make all those little tiny wires? How do you actually get something that small? So the way it works is, it's kind of the reverse of what a projector does. So a projector, you might have, let's imagine you have a slide projector, if people even know what those are anymore. You have a little slide and you're projecting something, and there's a little tiny slide, and the projector projects out, and you have this great big image, in the front of the movie theater or something like that. So let's imagine you ran that in reverse. You had a big thing, but you were sort of demagnifying it. You were just, like with a bunch of lenses, you were just making it so that you go from a big image down to a tiny image. So what happens is, when you make a silicon chip, a microprocessor, what you're doing is you get this giant map that you actually, I don't know how they do it now, but they used to actually have these physical sheets of that were essentially drawings of the map in different layers, and they would take that giant drawing and they would essentially be just demagnifying it down onto this little tiny piece of silicon. And it turns out that the way it works is, usually it's done using ultraviolet light, but it could be done using visible light. What happens is, you take this image of the sort of cityscape that you want, and you project it onto this little chip, much demagnified, and in places where there's sort of a dark line. Okay, then another thing, you have a material that's on top of the silicon. I think it's photoresist, I think it's called, which has the property that when ultraviolet light falls on it, on a particular part of it, you can etch it away with acid. And when it doesn't fall, you can't etch it away. And so what happens is, this sort of giant picture of where you want all the wires is projected very small in ultraviolet light onto this piece of silicon, and essentially where there was a dark line, when the acid comes through, it will etch it away, and where there wasn't a dark line, it won't etch it away, let's say. And what that does is, it will essentially etch out that cityscape that you had, and it will create all those billions of little wires and so on. And that's basically how a computer is made. And what typically will happen is, you'll have this wafer of silicon. It's big, very, very pure silicon. And on that wafer, you'll make a whole bunch of little copies of that, of the microprocessor, of the CPU chip. Usually, not all of them will work. The big issue in making semiconductors is what's called the yield. The question is, what fraction of those little microprocessors that you make actually work on a single piece, a single wafer that you get out from a single piece of silicon. And usually, you make them all, you test them, you have little probes that come down and test them. You say, this one's working fine. You say, this one's working really well. We'll sell that one as a higher speed computer. This one is only working rather slowly. That's a lower speed one. It's kind of like mining, different sizes of diamonds or something. But anyway, so that is a really long description. Sorry, that took a long time. Computers are complicated. I mean, there's more to say about how computers work, but that's at least a first approximation. We're going from, all the data that, including programs, are turned into these bits. They're stored in the memory. They are the things are being extracted from memory according to the instructions in the machine code. run through the ALU, which actually does the computations. The computations are done using these circuits that are made out of NAND gates. That's kind of how computers work. All right, let's see. That was really long. Let's see. There's a question here. Okay. Is there a limit to how many dimensions you can have? Very different question. No, there's no limit. Just like I was saying that every corner of our hypercube can have, let's say in 4 dimensions, can have 4 neighbors, you can have a 1,000-dimensional hypercube. It has 1,000 neighbors to every corner. And okay, if you want to get really fancy, you can say, what's the limit of a hypercube as it has an infinite number of corners? That's a complicated thing. It's well, it's kind of like a Hilbert space. It's kind of like a Cantor set. It's a bunch of fancy math. Some aspects of which aren't very well understood. But yeah, you can have at a mathematical level, you can have a thing with any number of dimensions. Next question: what is 0.2 dimensions? Let me not. This is going to get us into a long discussion of things called fractals. Maybe we'll come back to that. Let me keep going a little bit on some of the other questions here. Okay, we got a question from Klaus. Why do you have to acquire a certain speed to escape Earth's gravity to get into space? Okay. Well, let's first of all say what's true, and then I'll try and say a little bit about the why. So, first thing that's true, the escape velocity of the Earth is 25,000 miles per hour. That means if you threw something up, assuming you ignore air resistance and so on, if you throw a rocket up, if you make a rocket go up more than 25,000 miles an hour, it will escape the Earth's gravity and it can go floating off into the solar system. If it's less than that, if it has a speed less than that, it will eventually turn around and come back down again and come back down to the Earth. It might go into orbit if you've changed its orientation. It might go into orbit around the Earth. But the speed you need to get it to escape the Earth's gravity, to get out of orbit, to just go away from the Earth is 25,000 miles an hour. For the sun, it's 100,000 miles an hour. So the sun is there's more gravity associated with the sun. Its escape velocity is around 100,000 miles an hour. Probably the biggest thing I know is the escape velocity of the galaxy, which is around 1 million miles an hour to escape our galaxy. Good question is what the escape velocity of the universe is. And I kind of suspect the escape velocity of the universe is the speed of light, but I'm not immediately able to validate that. Oh yeah, I think that has to be true. The escape velocity of a black hole is the speed of light. And I think it's also true if you were to be sort of, in some sense, outside our universe. But I have to think about some fancy math to figure that out for sure. But anyway, so for the Earth, why is there a certain speed you need to go? Okay, gosh, different ways to explain this. You know, when you ask a question about why in physics, it usually just regresses back to being another, you know, eventually you end up with some physical law that is just, you're just told that's just true about the world. So because I've been working on fundamental physics, I'm sort of hoping we can do a little bit better than just go back to a physical law and say that's just true about the world. And actually, in my kind of approach to fundamental physics, I think we would have a slightly more elaborate answer to this question of why. But I'll tell you the traditional physics answer. The traditional physics answer would be this. There is a certain force of attraction between objects that have mass. It's a force of attraction that's the result of gravity. And that force of attraction, it's an inverse square law. As you make the things twice as far apart, it's 2 squared less force, a quarter the gravitational force. So the what's happening is that you are, well, let's see. I mean, the usual physics way to say it would be that the potential energy associated with gravitation you need to overcome that by having kinetic energy associated with motion. Essentially, what you're doing is you're saying it's as if you were being, what's the best way to say it? You know, all of these things are really just going to come back to saying it works that way because there's gravitational force, and in order to escape that gravitational force, you have to have a certain kinetic energy, a certain velocity. You know, I think there's probably a better way to do this, but it's going to take me a few minutes of flailing around here to get the optimal explanation that involves minimum math, and I'm not sure I'm going to be able to do that. Let's just say that it's easy to work out if you know the formulas for how the acceleration due to gravity and how that compares to that generates a gravitational energy that you have to overcome. The way people think about it is, it's usually one says that things have gravity wells. It's as if there's kind of you're being sort of, there's this area that has sort of gravitational, where you're kind of at okay, there is a way to explain this using general relativity, which might be a little bit more of a why answer. Let me punt on this for right now. Let me keep going, because otherwise I'm going to get trapped in this particular gravity well for a long time here. So let me keep going. All right, there's a question from Luis on Facebook. This is a slightly mathy question. It says, I've seen Gaussian primes, which are two-dimensional primes. What's the equivalent in 3D? Okay, I'll answer this, but I'll answer it fairly quickly because the answer is going to be kind of complicated. So I talked about prime numbers, and prime numbers are numbers that have the property that you can't divide them by anything other than themselves. So a number like 7, as opposed to a number like 8, where you can divide it by 2 and so on. Okay, when it comes to complex numbers, which I'd be happy to explain sometime, but I'm not going to explain today, you have, well, complex numbers involve having things like the square root of -1 added to your ordinary numbers. There's a notion of primes for complex numbers as well, but the result, the fundamental theorem of arithmetic, that there's a unique factorization. Am I misremembering this? I don't think that applies to Gaussian primes. It doesn't apply. So there isn't just one way that you can take a complex number, complex integer, and write it in terms of complex primes. But that's what the Gaussian primes are. They're writing a complex number like 3 plus I. They're asking, can you write that as a product of other complex numbers? And so the question is, what's the analog? Complex numbers are a way of representing sort of pairs of numbers, real and imaginary part of a number in 2 dimensions. What's the analog in more dimensions? It's quite complicated. So there are things called quaternions, which effectively are like 4-dimensional things. And there are things called octonions, which are kind of like 8-dimensional things. And after that, you lose it. The properties of that relate to these so-called number fields no longer apply. There are properties that sort of allow you to do things like prime factorization, but they don't apply anymore. And there's a pretty elaborate theory of how all that works. Even for the quaternions, the notion of primes is complicated, and I think not all that well studied. So it gets very complicated very quickly. And if you ask for the pure 3-dimensional case, there isn't really a pure 3-dimensional case. Just to say one quick thing, if you look at relative primality, you can ask, when is the GCD of 2 numbers equal to 1? I'm getting complicated here. You can say, you can talk about that in terms of triples of numbers, and that's a way that you can get something like primality in 3 dimensions, but that's a relative primality idea. Okay, next question here. Somebody's wondering about exporting from Mathematica 3D plots into virtual reality. Actually, I think that works rather. The real problem with virtual reality, so virtual reality, for people who don't know, is, you wear this, typically in the good version, you wear this big headset, and it's showing you an image in each eye, and because it's showing you potentially a different image in each eye, things really seem 3-dimensional. Normally, when we're looking at a computer screen, we are looking at the same image with both eyes. And so because the way that we perceive things in 3 dimensions, more or less, uses the fact that we're seeing the things from slightly different angles from our 2 eyes, and that's why our brain kind of sort of synthesizes that into, oh, that's a 3-dimensional object. Well, we can simulate that in virtual reality by having a slightly different image in each eye. It's sort of challenging because there are, the way it works is a VR headset has an accelerometer in it, so it knows when you're turning your head, and it can figure out how to sort of make the image be locked in place, even though you're turning. But you can be able to see different things as you turn your head. Unfortunately, if there's even the slightest lag, and when you turn your head and when you see a different image, it produces some kind of motion sickness. And actually, for me, I have a really hard time using virtual reality stuff for more than a few minutes because it makes me motion sick. And I've been, for the project that I've been doing about fundamental physics, part of that, it's really useful to be able to look at things in virtual reality. And I didn't expect it to be kind of an occupational hazard of doing kind of basic physics research that I would get motion sick in virtual reality, but I've been finding that. But the problem is that in virtual reality, to specify objects in 3 dimensions, and particularly to specify how the objects relate to each other, is kind of complicated. And so, I mean, this is again sort of techie fact. There isn't really a great standard for how 3-dimensional objects are represented in virtual reality. There are standards for 3D graphics, and like in Mathematica, we support all of those kinds of things. But the most common thing is using this system called Unity, which is essentially a game-making system, and putting things into Unity. And we have a really good system for doing that from Mathematica. Okay, that was a complicated question. Let me see what. Oh boy, we've got. Okay, we're nearing the end of our time here, but let me look at a few other things here. There's a question from Ettore here. Can we do computation not based on silicon technology? What really is computation? Boy, you shouldn't get me started on that. I've spent half my life studying that question, at least the second part of that question. What really is computation? I talked about how in computers, you're just doing these logic operations with nands, and you're moving ones and zeros around, and you've got these different opcodes and operations that the computer does. Turns out you don't need anything like that complicated to make a computer. I'll show you one of the simplest computers I know. Let me pull something up here. This is actually a thing. Let me share this. Hold on one second. This is the simplest computer I know, and actually in many ways the simplest computer that can exist. This was a prize I put up about 10 years ago for somebody. I had guessed that this was the sort of simplest possible computer, and this was a prize for proving that it really was a possible computer. And a young chap in England succeeded in doing that, and won the prize I put up. But this is a thing that just gives it's a thing called the Turing machine, named after a chap called Alan Turing, who invented these the general idea of these kinds of things in 1936. It's a very idealized computer. Instead of having electricity and all that kind of thing, it just has a line of little idealized cells, and each idealized cell in this case is either white, yellow, or orange, and at each cell it has this little head that is either up or down. And so Alan Turing invented this kind of idealization of computing, that you could do it in terms of just writing squares on a tape and having this sort of single place where you put squares on a tape. He actually invented that as a way of imitating what people who were bank clerks in those days used to do. You take something out of a file cabinet, you look at it, you do some operation, you write back an answer, you put it back in the file cabinet, and so on. He was kind of idealizing that in a more sort of theoretical way, and he came up with these things. He had much more complicated versions of it, but that boil down to this so-called Turing machine. So this particular, you can have lots of different rules for what you do when you can have a head that's in 1,000 different possible positions. This one is in just 2 different possible positions, states, or 2 different possible states up and down. You can have, instead of just 3 colors on the tape, you could have 100 different colors on the tape. But you could ask the question, what's the very simplest collection of a very simplest set of rules that would, in principle, allow you to make any computer, do any computation out of them? And this is the answer. We know it for a variety of other kinds of systems, not just Turing machines, but we know that in principle, you could make a computer just out of a sufficiently large version of this. And if you ran it sufficiently long, you could set it up so that the initial arrangement of squares of colors of squares on the initial tape was such that you could make it do any computation you want, in principle. It might take billions of steps and it might take billions of squares on the tape, but in principle, you can make it do any operation you want. And that's fact that you can do that is this idea of universal computation. And this is the simplest thing, that the simplest underlying computer that lets you do universal computation. So the question is, what could you implement this on? I mentioned that in silicon, it's very easy to implement NAND operations, or it's at least possible to implement NAND operations. So that's what all computers are based on. But let's imagine you had something where you could implement this little rule for a Turing machine. You could make a computer out of that. Well, it's a guess, we don't know it, it's a guess that you might be able to have a single molecule that you could make operate like this Turing machine. In fact, we already know that there are things a little bit like that. In every cell in our body, there is this, there's DNA, which stores our genetic code, our genetic program, but when that genetic code is transcribed, it turns into RNA, and then there's little things called ribosomes, which kind of walk up and down the RNA, kind of generating proteins to actually produce the things that make us up. And those ribosomes, well, they're not quite like Turing machines, but you could imagine them being made to be like Turing machines. They're like this head on the Turing machine that goes back and forth, back and forth. You could imagine something like a ribosome that will be sitting on a molecule going back and forth, and doing things. We don't know how to make such a thing right now, but one could imagine being able to make that, a molecular scale computer that operates using, for example, this particular universal computer. It's something I've spent some significant part of my life discovering sort of very simple ways to do computation, like this example for the Turing machine here. But one of the things that suggests is that you can make computers out of almost anything, and you could, for example, make molecular computers. I mean, right now, the only the best sort of molecular scale computer type thing that we have is basically us, our biology. I mean, effectively, biology can be thought of in many ways as like a molecular scale computer, and it's the only example we have really of that working. But we can certainly imagine in the future being able to make molecular scale computers that are sort of all of our own design. Some people think we can sort of piggyback on biology to use DNA to make computers. I don't think it's the best way to do it, but I think it'd be better if we could work from scratch and make our own molecules rather than having to have the molecule that we've been sort of delivered by the process of biological evolution over the last few billion years. So in any case, look, even at the level of ordinary computers, I should say that, that's very sort of futuristic computers made of, where the computers are happening at the level of individual molecules and so on. There are somewhat more prosaic versions, somewhat more simple-minded versions of that. So silicon is the most popular material to make computers out of. There are other things, gallium arsenide, germanium, are other materials that people have made computers out of. Another approach is what quantum computers get made out of. Those are often made, well, things called Josephson junctions, which are well, oh gosh, another thing I can talk about another time if people are interested are things called superconductors, which is what Josephson junctions are made of. All right, let's see. All right, I'm going to all right, I'll take two more questions, then I'm wrapping up for here. One is from Toma. What do I think about virus treatment advancements in the next 10 years? Will a pandemic treatment look different than today? What about general vaccines, better antiviral drugs, etc.? You know, there is one futuristic thing that might happen. Well, okay, first point is, in terms of vaccines, I think I talked about previous time some things about how vaccines work. But essentially, a vaccine has to present to your immune system something that looks like enough like the virus that your immune system will react, produce antibodies, produce the things it needs to fight the virus if the virus showed up for real. And one of the things that people sort of hope is that maybe there'll be a sort of universal vaccine that has a universal across a certain class of viruses, because there are certain pieces of the virus that are pieces of its of the proteins it contains, the RNA it contains, that are things that never occur as pieces of the cells that make up our bodies, but only occur in viruses. And if we could make sort of a vaccine that says, if ever anything that looks like this, if ever a sequence of amino acids or a sequence of a piece of a RNA or something shows up that looks like this, go attack it. If we could find a thing like that that existed on a bunch of viruses but didn't exist on other cells in our bodies or other kinds of cells that we care about, if we could make a vaccine that just says, anytime you see this, you know, make the immune system fight it off, then that would allow us to have a more universal vaccine. Now, it's not realistic to do that across all possible viruses, because viruses don't share, they don't universally, it's not like there's a thing that says on the RNA sequence or the DNA sequence of a virus, there's not a little piece of it that says, I'm a virus and nothing else. Each different kind of virus has a different sequence. The one that we're fighting right now has just 29,000 bits, effectively double bits in its sequence. And so, but among the class of, let's say, influenza viruses, coronaviruses, whatever, those classes of viruses, there might be the possibility of having something which says, every influenza virus, we have a thing that shows up in every influenza virus, and we mount an immune response. We set it up so that an immune response will be mounted whenever something which is just that piece of, just that thing which exists in all influenza viruses, regardless of whether it's an H1N1 or a, whatever it is, a different detailed flu virus shows up. So that's one approach. A more out there approach is something that, so how do drugs typically work? So drugs are typically molecules that have a chemical activity with respect to some molecule that exists in us. That's the most common kind of thing. So what typically happens is we are made mostly of proteins, which are these big, long molecules. And the big, long molecules have all kinds of complicated shapes. And the first approximation, a lot of drugs work by finding some particular piece of that shape where the drug molecule just fits into that shape. There are other ways that some other kinds of drugs work, but I think there are only about 1,800 kinds of drugs that are the officially approved collection of drugs that exist in the world. And of those, a decent fraction work the way that I'm saying. They're these long protein molecules, they have all these complicated shapes. The drug molecule is the right shape to stick itself into some opening or something in the protein molecule. And what that will do is it will, for example, stop that protein from working, or it'll make the protein work. It'll do things like that. They block the operation of the protein, or they enhance it, or something like that. And they do it in this very physical way. The molecule is floating around, and it finds, it's like kind of a lock and key type thing. The molecule sees that it can attach to what's called the binding site, and it will then lock into the molecule that it's trying to deal with and do a particular thing. And so, for example, we might do that. So that's the typical way that existing drugs work. They're these molecules, they fit sort of mechanically into things like proteins. Okay, so there's another bizarre thing you might be able to do that actually relates to what I was just talking about molecular computers. What if that drug molecule was a little computer? And what if instead of just saying, instead of just floating around and if it's the right shape, it fits, imagine that that molecule could actually, in a sense, sense its environment, do a computation and say, hey, I don't like this particular cell. It looks like it's been infected by a virus. I'm going to go attack it. Let's say that it could actually compute things. It could make measurements on the cell, and it could say, okay, it's got this feature, and that feature, and therefore I'm going to do a piece of logic to say, so that means that cell is one that I should attack. Let's say you could make essentially an algorithmic drug or a computational drug, a molecule that isn't just a static molecule that binds to things, but a molecule that actually computes what to do based on what it finds. Now, at some level, things like the T cells in our immune system are doing something a little bit like that. But we could imagine that's sort of the ultimate antiviral type thing would be something that can really do logic in a way that kind of enhances the logic that can be done by our immune system to figure out how to attack things. And potentially, our immune system has to learn to attack things by essentially a process that's like biological evolution, that's like natural selection. In us, over the course of time, we are sort of growing a collection of cells that are optimized to attack the things that we expect to attack us, the things that we've been vaccinated against, or the things that we've seen before, and so on, that we've decided are bad molecules, and so on. So, yeah, Sandra on our live stream is commenting that at some point we should be able to have little mini robots in our blood that could be reprogrammed to search and destroy particular intruders. Yes, I think that's what will eventually happen. And it'll be an interesting thing because, I mean, at some level, things a little bit like that are being done with some cancer treatments now. But it's a long story how all of that works. I'd be happy to talk about it. And it's a little bit related to how CRISPR and gene editing type complicated story. Let's not get into that another time. All right. And, this question about better virus testing and so on. I mean, the way that, we're testing for the current, let's not get into that. I can talk about how the different testing methodologies are working now and what might be possible in the future. I'm going to do one more question here, which is, do scientists always use metric units? I was talking earlier about the Babylonians from 4,000 years ago. They were the first folks that we know of who sort of systematized things. And before that time, there were, and part of the reason they did that systematization is because they were building cities. And as soon as you have a city, you need to be able to do things like say, what's the area of this piece of land and how does it compare to that? And you need to have money where you're counting things. You need to say this amount of barley costs this amount, and this, how big a volume of barley do we have? Well, in the past, sort of every city would have its own system of units. And even 150 years ago, there were different units. There was the, the Berlin system of units, the London system of units. And you see that particularly with amounts of mass and volumes of things. And even there were different units for, a mass of bananas versus a mass of grapes versus whatever else. Each different thing had its own units, and each different city would have its own system of units. It's a little bit like in today's world with money. Different countries have different currencies. You can convert between them. Those conversions, in the case of money, because it's a slightly more complicated kind of thing, those conversions float and change. In the case of, I have this load of bananas, it better be the case that that load, I shouldn't use the word bananas because it really plays to my British accent and sounds weird in American, but let's say oranges, apples. We have this load of apples, and And it better be the case that that load of apples that weighs, 25 London pounds, and it weighs 23 Berlin pounds, and so on. That's very confusing because you have to say, London pounds, Berlin pounds, and so on. Anyway, the first time any of that stuff was systematized that we know of was by the Babylonians. But then over the course of time, different places systematized differently. And there was the so-called imperial system of units. The system of units that was promoted by the British Empire was the system of units that we have of miles, inches, feet. I remember when I was a kid, I grew up in England, and one of the things, England doesn't have a constitution like the US Constitution or something. They did have a thing called Magna Carta, which was drawn up by a chap called King John when he was trying to get his barons to kind of be happy and let him go on being king. He had the thing called Magna Carta, which was the sort of the rule, the laws of the land or something. And one of the things that always confused me when I was a kid, I knew one of the provisions of Magna Carta is that an inch would be the length of the king's thumb. And I always was very confused by that, because it was like, well, what if there's a different king? What if, how does it, well, of course, actually King John probably had a much smaller thumb than our modern inch. So it was a fictional king's thumb, but nevertheless, it was, that was kind of an attempt to standardize units in England with an inch as the length of the king's thumb. Okay, but so the system of units that was used in the countries that were in the British Empire, which included the US back a long time ago, were the imperial system of units, which were miles, feet, pounds, all those kinds of things. There was an attempt, so in France, when Napoleon was in power in France around 1800, he decided to commission a new system of units, the so-called metric system of units. And so he tried to invent a sort of a perfect system of units. And his approach was, for example, the meter was defined relative to the Earth. And a meter, I think, is if you take the great circle that goes through Paris and goes around the Earth through the North Pole and the South Pole and through Paris. I think a meter, if I'm not mistaken, is 1/1,000,000th of the circumference of that circle. If I'm not mistaken, I might have that off by a little bit. But so that was the definition of a meter that Napoleon made, and that was the metric system that it was invented by Napoleon. And the metric system had a lot of good features. For example, everything was base 10, and it was in the British system. Okay, in the British system, there were British system of units. There are 12 inches in a foot, 3 feet in a yard, 1760 yards in a mile. It's a total mess of different kinds of numbers. The Babylonians often used base 60. For some reason, in the British imperial system, there were these different factors. Even money used to work that way. When I was a kid in England in the 1960s, money worked this way. There were pennies, the equivalent of cents in American cents, pennies, and there were 12, my gosh, am I forgetting this? There were 12 pennies in a shilling and 20 shillings in a pound. Okay, so it was a non-base 10 system of units. And I used to say, actually, I remember telling some teacher of mine when I was about 6 or something years old, I said, this is really stupid. There's no reason to do it this way. You could perfectly well have money work with multiples of 10. And this teacher said, no, it's been that way for 1,000 years. It's going to be that way forever. And I was like, really? And it turned out just 2 years later, Britain announced that it was going to decimalize. It was going to turn its money into being base 10 money. That eventually happened in 1970. It was actually interesting. I mean, this is neither here nor there, but it might be amusing for people. What happens when you do something like change the money from being non-decimal, not based on tens, to being decimal? And I remember they were running these television programs about decimalization. where they were trying to, for about a year beforehand, explaining to people, this is how it will work. And they were very worried about people are going to be confused, and et cetera, et cetera, et cetera. And then there was this actual day when the non-decimal money went out of circulation, the decimal money came into circulation. And it was kind of cool because, you know, you got given this old money and you get back the new money. And the thing which was most notable to me was people were not confused. People were very unconfused very quickly, which wasn't necessarily, I wouldn't necessarily have expected it to work that way. I thought, you know, people might have been confused for a long time, but they weren't. It was very, very fast. But so in the system of units, the imperial system of units that's used in the US, in England, it's not decimal. It's not, it is for money now, but it's not decimal for things like lengths and masses, weights, and so on. And that's awfully inconvenient when you're doing sort of mathematical type calculations. I might say the following. One of the things that I thought was interesting about the decimalization of English currency, it happened in 1970. I actually mentioned earlier in this discussion that calculators came in roughly in 1970. And I actually believe that if calculators had, if Britain had delayed decimalizing money for even another 2 or 3 years, it would never have been decimalized, because doing calculations with non-decimal money is a big nuisance, big mess. But if you'd had calculators to do it, everybody would have been able to do it easily. And so I suspect that there wouldn't have been any motivation to decimalize the money, because the real reason to decimalize was to make it easier to do the calculations. So the original question here was, do scientists always use metric units? The answer is pretty much yes. I mean, there are some other kinds of units used in some areas of science, but in most areas of science, it's convenient to use decimal units. Areas where it isn't, in astrophysics, sometimes there are units like light years and parsecs that are used, which aren't really decimal in that they're not part of the standard unit system. I mean, the thing to understand is that all the units for different kinds of things, you know, the units of volume, the units of, there are a certain number of basic units that you have to specify. And so, in fact, in the standard way it's done, it's the meter, the kilogram, and the second. The units of mass, length, and time are sort of the most fundamental units. Strangely, there are a few other fundamental units: the unit of amount of substance, number of atoms in a mole, unit of luminous intensity. There are all sorts of arguments now about whether angles should be fundamental units. But fundamentally, the three units that are, the three kinds of units that are really fundamentally used are mass, length, and time. And you can derive other things, like volume is length times length times length, length cubed, that's the units of volume, and so on. So you can derive other units, but in the sort of the most basic units that you have to have are a unit of length, a unit of mass, a unit of time. If you get into fancy, well, no, let me not go there. In fundamental physics, there's some new thinking about how that might work. But my final parting thing here is, like, how do we measure in modern times? You know, back in the days of Magna Carta, we measured length in terms of, supposedly in England, the length of the king's thumb. How do we measure length, mass, time now? They're all actually measured in terms of features of atoms. Until very recently, until just a couple of years ago, the way that kilograms were ultimately measured is using a particular metal kilogram that was sitting in a vault in Paris, I believe. That was the kilogram, the standard kilogram, and there were copies of it in different places. And if you wanted to know absolutely for sure that you have exactly 1 kilogram of mass, you could in principle go and take that thing out of the vault in Paris and find out if it was the same mass as the thing you had. I think it got taken out of its vault once a decade or something, and it had to be very carefully controlled. But anyway, it's much better to measure everything in terms of properties of atoms, and that's what is now being done. Everything, mass, length, and time, are all measured in terms of properties of atoms, properties of atoms together with the speed of light. And the reason that's a good thing is because every, let's say, atom of cesium, or atom that happens to be one that's used, but every atom of carbon or whatever every single atom of carbon is exactly the same. It's a remarkable feature of physics that, you know, it's not the case. If you have a big lump of metal, there are lots of different lumps of metal we can make, but every single carbon atom that exists in the universe is essentially the same. And that means that if we use it as our way to make measurements of things, like we use it as our unit of mass, for example, it's this number of carbon atoms or something. It's not quite how it works, but let's say it was that. Then we can be sure that wherever we make this measurement, it will always be the same. And as I'm saying that, I'm realizing that I really should be qualifying that in terms of things about the effects of gravity and general relativity and all kinds of fancy things like that, which we're not going to talk about here now. All right, well, that was fun for me. I hope people found that interesting. And I will potentially do more of these. Please give us feedback on what was useful, what wasn't. I'm actually, this Thursday, I'm going to do something a little bit like this. I'm going to talk specifically about physics, and I'm going to talk about the history of physics. Okay, the very careful observer will realize that maybe I'm talking about the history of physics because I'm hoping next week to talk about more things about the future of physics. But anyway, this week I'm going to talk about the history of physics, and I'll try and give a kind of an outline of kind of the whole history of physics from antiquity to sort of the present day. And that will be, I hope, at a fairly elementary level, and be happy to have questions and things there. Thanks for coming today, and I'll sign off from this. Okay.